we start with the definition of vector space. A set S is called a vector space over a field F if it satisfies the following conditions. First, the set has two operations, vector addition and scalar multiplication, defined on it. It means that the addition is defined for any two elements of the set and the result of the addition is again an element of the same set. Multiplication is defined for a scalar from the field F and an element of the set S, and the result of the multiplication belongs to the set S. This is also called closure property, or we say that the set S is closed under vector addition and scalar multiplication. Second, vector addition should be commutative. For any two elements x and y of the set S, x plus y and y plus x should be equal. Third, vector addition should be associative. If we have three vectors, we can add them together by first adding x and y and then adding z, or first adding y and z and then adding x into it. These orders of addition should result in the same element. Fourth condition is about existence of the additive identity. The set S should have an element E such that adding it to any element of the set S does not change the element. The additive identity is also called a zero vector. It is denoted by a small letter E or a bold-faced 0. It is analogous to the real number 0. Fifth condition, every element of the set S should have an additive inverse. The definition of additive inverse is that if we add an element to its additive inverse, the result will be the zero vector. Since the addition is a commutative operation, x and y are additive inverses of each other, meaning that if y is the additive inverse of x, then x is an additive inverse of y. Fifth condition requires that the set S should contain an additive inverse for every element. If we can find an element in the set S whose additive inverse does not exist, the set S will no longer be a vector space. Additive inverse of an element x is denoted by x with a negative sign. Do not confuse this with multiplying x with -1. It is just a matter of representing additive inverse with a negative sign. Sixth, there should be a multiplicative identity so that if we multiply it with any element of the set S, the resultant element should not change. Multiplication is defined for a scalar and a vector, and addition is defined for two vectors. So the additive identity belongs to the set S and the multiplicative identity belongs to the field of scalars. Please keep in mind that here 1 does not mean the integer 1. Even in some cases, the field of scalars is not the set of real numbers or set of integers. We just represent multiplicative identity with the symbol 1. Seventh condition is that scalar multiplication should be associative. If we have two scalars and a vector, multiplication of the scalars with the vector in these two orders should be equal. Eighth condition requires that multiplication should be distributive over addition. If we have a scalar a and two vectors x and y, multiplying the scalar with the addition of x and y should be equal to the addition of ax and ay. And if we have two scalars a, b and one vector, the multiplication of a plus b with x should be equal to the addition of ax and bx. If a set is a vector space, it has all these 8 properties. To remember them easily, let's divide them into 3 groups. First group says that vector addition and scalar multiplication should be well defined and the set under consideration should be closed under addition and scalar multiplication. Second group is about commutativity and associativity of addition and the existence of additive identity and additive inverse. And the third group is about associativity and distributiveness of scalar multiplication and the existence of multiplicative identity. Let's look at an example. The set S contains all the ordered pairs of real numbers with pairwise addition and scalar multiplication. We will verify that the set S satisfies all the 8 conditions. Clear property. Suppose x and y are any two elements of the set S, then x and y are ordered pairs of real numbers. We add x and y according to the definition of addition. Since the addition of two real numbers is also a real number, therefore x plus y is also an ordered pair of real numbers and thus belongs to the set S. So the set S is closed under vector addition. Let's now verify the clear property with respect to the scalar multiplication. Again, suppose that x is an element of the set S and A belongs to the field of scalars, which is the set of real numbers in this case. X is an ordered pair of real numbers. Multiply A with x. Now A times x1 and A times x2 are also real numbers, so the resulting element is also an ordered pair of real numbers. Therefore, Ax also belongs to the set S and the set S is closed under scalar multiplication. The set S is closed under both operations of vector addition and scalar multiplication. We verify commutativity of vector addition. Suppose x and y are two elements of the set S. Add x and y. x1 plus y1 and x2 plus y2 are the usual additions of two real numbers, and we know that the addition for real numbers is commutative. So we can change the order of addition of x1 y1 and x2 y2. But this is equal to ordered pair y1 y2 and ordered pair x1 x2, which is equal to y plus x. So the vector addition is commutative. Now we verify that vector addition is associative. Again, x, y, z are three elements of the set S, so these are ordered pairs of real numbers. I start by adding x, y, z in this order and will show that it is equal to x plus the addition of y and z. Add x and y together and add z. Now x1, y1, z1 and x2, y2, z2 are all real numbers, and we already know that the addition of real numbers is associative. So we can change the order of addition like this. This is equal to x plus the addition of y and z. We further separate y and z, and this is equal to x plus the addition of y and z. Vector addition is associative and the set S satisfies third property as well. Let's see if the set S contains additive identity. This is a slightly simple example of a vector space, and one can easily identify that the ordered pair 0, 0 is the additive identity or the 0 vector. Let's check it. Suppose x is an element of the set S. Let's add x to the 0 vector. Add them element-wise and the result is again the vector x. The set S satisfies the fourth condition of having an additive identity. Now we verify that each element of the set S has an additive inverse. Again, suppose x is an element of the set S, then the ordered pair with the inverted sign also belongs to the same set. Because x1 and x2 are real numbers, and therefore minus x1 and minus x2 are also real numbers, and an ordered pair of real numbers belongs to the set S. The ordered pair with the inverted signs is the additive inverse of x. Let's add them together to see if their addition is the 0 vector, and in fact it is the 0 vector. Additive inverse for every element of the set S exists. The set S satisfies the fifth property as well. Existence of multiplicative identity. The real number 1 is the multiplicative identity. Let's verify it. X is any element of the set S. Multiply 1 with x and the resulting element is again equal to x. Multiplicative identity exists. I again emphasize that the multiplicative identity is a scalar and belongs to the field of scalars, which is the set of real numbers in this case. But the additive identity is a vector. Let's verify the seventh condition that the scalar multiplication is associative. Suppose x is an element of the set S and a and b are scalars. Multiply the product of a and b with x. Now a, b, x1 and x2 are real numbers and we already know that multiplication for real numbers is associative. So we can safely change the order of multiplication without affecting the underlying ordered pair. By using the definition of multiplication, we can take A out of the ordered pair. And likewise, we can also take B out of the ordered pair. But this statement is equal to this. The set S satisfies the seventh condition that the multiplication is associative. Eighth and the last property, which is about distributiveness of the multiplication over addition. Let's verify it. X and Y are any two elements of the set S, and A belongs to the field of scalars. Multiply A with the addition of X and Y. First add vectors X and Y using the definition of the addition of two vectors. Now multiply A using the definition of the multiplication of scalars. A, x1, x2, y1 and y2 are all real numbers. Therefore, we can distribute A over the addition of x1 and y1 as well as over the addition of x2 and y2. By definition of the addition of two vectors, we can write the ordered pair as a sum of two ordered pairs. And from the definition of multiplication of scalars, we can take A out of the ordered pairs. And the final result becomes what we are looking for. It is AX plus AY, and hence first part of the distributive property is verified. We also need to verify the distributiveness of the multiplication in the case of one vector and two scalars. X is a vector and A and B are scalars. Multiply the sum of A and B with the vector X. Using the definition of multiplication, multiply A plus B with x1 and x2. As A, B, x1 and x2 are real numbers, we can multiply them like this. Write the resulting ordered pair as a sum of two ordered pairs. Using the definition of multiplication, we can take A and B out of the ordered pairs, and this is equal to AX plus BX. So the second part of the distributive property is also verified. The set S has all the 8 properties, and therefore it is a vector space over the field of real numbers with the given addition and multiplication operations. The smallest vector space is a set consisting of only the identity vector. All the 8 properties are trivially satisfied by this set. This example is a generalization of the ordered pair example. Here the set S consists of ordered and tuples of real numbers. The addition and the multiplication are defined the same way as in the case of the ordered pair example. These are pairwise addition and scalar multiplication. All the properties of vector space can be verified on the same lines as we had done in the ordered pair example. Any vector in this vector space can also be written as a column vector. The identity vector is the ordered n tuple having all zeros or a column vector with n zeros. The inverse of X is the vector whose entries have the inverted signs. In this example, the vector space consists of matrices of order m cross n. All the matrices with m rows and n columns are vectors in this vector space. The set is a vector space over the field of real numbers with usual matrix addition and scalar multiplication. If A and B are any two matrices of order m cross n, the order of A plus B as well as the order of scalar multiple of A is again m cross n. So the set is closed under vector addition and scalar multiplication. We already know that matrix addition is commutative and associative. The zero matrix having m rows and n columns is the identity vector in this vector space, and the inverse of the matrix A is the same matrix A with entries whose sign is inverted. The real number 1 is the multiplicative identity. It is also very easy to verify that the scalar multiplication is associative as well as distributive. Let us look at an example of a set which does not satisfy the conditions of being a vector space. It is the same set of ordered pairs of real numbers. The field of scalars is the set of real numbers. Scalar multiplication is defined in the same way. However, vector addition is slightly modified. Instead of a2 plus b2, we multiply a2 and b2 in the definition of vector addition. Now let us see if the ordered pair 0, 0 is the identity vector or not. Let us add it to an ordered pair, and the resulting ordered pair is not the same. So the ordered pair 0, 0 is no longer the identity vector in this case. What is the identity vector for this set under the given addition operation? Let us dig deep and find out the identity vector. The identity vector xy should be such that if we add it to the ordered pair a1, a2, the ordered pair should not change. Using the definition of addition of vectors, let's perform addition on the left hand side. Now, two ordered pairs are considered equal if the corresponding entries are equal. a1 plus x should be equal to a1 and a2y should be equal to a2. And from these two equations we have x equal to 0 and y equal to 1. The ordered pair 0, 1 is the identity vector. So the additive identity exists. Now let us try to check if the additive inverse of every element exists or not. By definition of additive inverse, an ordered pair xy is the additive inverse of the ordered pair a1, a2 if their addition is the identity vector, which is the ordered pair 0, 1 in this case. Perform addition on the left hand side using the definition of addition, and the corresponding entries should be equal. a1 plus x should be equal to 0 and a2y should be equal to 1. From these two equations we have x equal to minus a1 and y equal to 1 by a2. So apparently the ordered pair minus a1, 1 by a2 is the additive inverse of the ordered pair a1, a2. But hold on. Does additive inverse exist for every element? What is the additive inverse of the ordered pair 5, 0? Is it the ordered pair minus 5, 1 by 0? But 1 by 0 is undefined. We cannot divide any number by 0. So all the ordered pairs with the second entry equal to 0 have no additive inverses in the set S. Therefore, the set S with the given addition and multiplication operations is not a vector space because every element does not have an additive inverse in the set. Cancellation law for vectors says that if x plus z is equal to y plus z, we can cancel out z and conclude that x is equal to y. And likewise, we can infer the equality of x and y if z plus x and z plus y are equal. Let us prove this law. Suppose x plus z and y plus z are equal. Now, V is a vector space, so additive inverse of every element exists. Particularly, additive inverse of z also exists. Add additive inverse of z on both sides, and by using associative law of vector addition, we can change the order of addition of three vectors. Now, addition of z and its additive inverse is the identity vector. Therefore, x plus 0 vector is equal to x and y plus 0 vector is equal to y. We can prove second part of the cancellation law on the same lines. In a vector space, the identity vector is unique. A vector space has only one identity vector. And secondly, every vector in a vector space has exactly one additive inverse. Let us prove these two statements. We start by assuming that a vector space has two identity vectors, and we will conclude that these two identity vectors are equal. Suppose 0, 1 and 0, 2 are two identity vectors in a vector space. This implies that x plus 0, 1 is equal to x as well as x plus 0, 2 is equal to x. It means that x plus 0, 1 is equal to x plus 0, 2. But from the cancellation law, this leads to the equality of 0, 1 and 0, 2. Now, we prove that additive inverse of every element is unique. Suppose a vector x has two additive inverses, y1 and y2. This means that x plus y1 is equal to 0 vector and x plus y2 is also equal to 0 vector. This implies that x plus y1 is equal to x plus y2. And from the cancellation law, we can conclude that y1 and y2 are equal.